Welcome to an in-depth scientific lecture on catalytic microtubular nanomotors, revolutionary man-made nanomachines that self-propel in chemical fuels. These tiny tubular structures represent the first successful autonomous nanomachines, capable of converting chemical energy into mechanical motion at the nanoscale. This groundbreaking discovery was made by Professor Alexander Solovev and established an entirely new field in nanotechnology. This achievement earned a Guinness World Record in nanoscience, recognizing the fastest man-made nanomachine ever created. Let's begin by understanding what these remarkable devices actually are and how they function. Catalytic microtubular nanomotors are self-propelled tubular structures with dimensions ranging from hundreds of nanometers to several micrometers. They are powered by the catalytic decomposition of chemical fuels, most commonly hydrogen peroxide, converting chemical energy directly into mechanical motion. Typical dimensions are 1 to 10 micrometers in diameter and 5 to 50 micrometers in length, making them truly nanoscale devices. Here we see a schematic of the tubular structure, with an outer catalytic platinum layer and an inner titanium layer, forming a rolled-up bilayer tube. The fabrication of these nanomotors relies on an elegant technique called rolled-up nanotechnology. The process begins with depositing thin metallic films on a substrate, followed by selective etching of a sacrificial layer. Built-in mechanical stress in the bilayer films causes them to spontaneously roll up into tubular structures upon release from the substrate. The flat bilayer film on the substrate rolls up into a tube when the sacrificial layer is etched away, driven by the strain mismatch between layers. The rolling radius depends on the film thickness h and the strain epsilon, given by R equals h over 2 epsilon. For typical values of strain around 1% and thickness 50 nanometers, we obtain rolling radii around 2.5 micrometers. Now let's explore the fascinating propulsion mechanism that drives these nanomotors. The key propulsion mechanism is the catalytic decomposition of hydrogen peroxide at the platinum surface. Two molecules of hydrogen peroxide decompose on platinum to form two water molecules and one oxygen molecule. An important question arises. How does this chemical reaction actually create directed motion of the nanomotor? Hydrogen peroxide molecules diffuse to the platinum surface where they decompose, producing oxygen bubbles that propel the tube forward through bubble recoil and self-electrophoresis. The answer is that multiple mechanisms work together, including bubble propulsion, self-electrophoresis, and interfacial tension gradients. Among these mechanisms, self-electrophoresis is the primary propulsion mode in dilute fuel solutions. At the platinum anode, hydrogen peroxide oxidizes to oxygen, protons, and electrons. At the titanium cathode, hydrogen peroxide is reduced using the protons and electrons to form water. This asymmetric electrochemical reaction creates an electric field along the tube axis. The electric field E points from positive platinum to negative titanium, while the tube moves in the opposite direction due to electroosmotic flow. The velocity is given by epsilon r epsilon 0, zeta E over eta, where zeta is the zeta potential and eta is the dynamic viscosity. Typical velocities range from 100 to 300 micrometers per second, remarkably fast at this scale. To understand the physics at this scale, we must consider the Reynolds number and velocity scaling. The Reynolds number equals rho VL over eta, where rho is density, V is velocity, L is length, and eta is viscosity. For our nanomotors, the Reynolds number is approximately 10 to the minus 3. Meaning viscous forces completely dominate over inertia. What does this extremely low Reynolds number mean for the nanomotor motion? It means viscous drag completely dominates, there is no momentum, and when propulsion stops, the motor stops instantly. The nanomotor is surrounded by viscous drag forces from all directions, creating a highly constrained motion environment. The drag force follows Stokes' law. F drag equals 6 pi eta RV, where R is the effective radius. The motor velocity shows strong dependence on the hydrogen peroxide fuel concentration. Velocity scales with hydrogen peroxide concentration to a power n, where n is approximately 0.5 to 1.0. This graph shows how velocity increases with fuel concentration, following a power law relationship that reflects the catalytic reaction kinetics. Higher fuel concentrations provide faster speeds, but eventually plateau due to saturation of catalytic sites and oxygen bubble formation. Typical experimental ranges use 1 to 15% hydrogen peroxide solutions for optimal performance. One of the most powerful features is the ability to control nanomotor motion using external magnetic fields. By incorporating ferromagnetic materials like nickel or iron during fabrication, we create magnetically responsive nanomotors. A nickel segment embedded in the tube aligns with the magnetic field, allowing precise directional control of the nanomotor trajectory. The magnetic torque equals the magnetic moment M cross product with the field B, causing alignment with the field direction. The magnetic force equals the gradient of M dot B, allowing us to pull motors toward regions of high field strength. This magnetic control enables precise three-dimensional navigation and positioning of individual nanomotors. Let's examine the remarkable speed records that earned the Guinness World Record recognition. The record speed achieved was over 3 millimeters per second, an astounding velocity for a structure just micrometers in size. Converting to body lengths per second, 3,000 micrometers per second divided by 10 micrometers equals 300 body lengths per second. How does this performance compare to biological molecular motors found in nature? This is the fastest man-made nanomachine ever created, exceeding most biological motors and establishing a new benchmark in nanotechnology. This chart shows the progression from early prototypes at 100 body lengths per second to optimized designs at 200, and finally, record-breaking speeds exceeding 300. Let's analyze the energy efficiency of these nanomotors from a thermodynamic perspective. The free energy released from hydrogen peroxide decomposition is minus 120 kilojoules per mole. The power dissipated by drag equals F times V, which equals 6 pi eta R versus squared. Let's estimate the efficiency for a typical nanomotor operating under standard conditions. The drag power is approximately 6 pi times 10 to the minus 3 times 5 times 10 to the minus 6 times 10 to the minus 8, giving roughly 10 to the minus 15 watts. What is the overall efficiency of converting chemical energy to mechanical work? The efficiency is quite low, around 0.01 to 0.1%, typical for microscale systems dominated by viscous dissipation. Beyond magnetic control, several other mechanisms provide directional guidance of nanomotors. Magnetic fields remain the most common and versatile control method, allowing real-time trajectory adjustment. Chemical gradients can guide motors through chemotaxis, where they move toward or away from specific chemicals. Light-activated steering uses photocatalytic materials to control propulsion direction through spatially controlled illumination. Multiple control options enable flexible guidance strategies, allowing nanomotors to navigate complex environments toward specific targets. One of the most promising applications is using nanomotors for cargo transport at the microscale. Nanomotors can capture and transport various cargo, including biological cells, nanoparticles, and drug molecules. Here we see a nanomotor with cargo attached at one end, being transported through solution using the motor's autonomous propulsion. For successful transport, the attachment force must exceed the drag force on the cargo. Even while carrying cargo, nanomotors achieve speeds of 50 to 200 micrometers per second, demonstrating robust propulsion. The biomedical applications of these nanomotors are particularly exciting and transformative. Nanomotors enable targeted drug delivery, carrying therapeutic agents directly to disease cells while minimizing side effects. They can perform microsurgery tasks and precisely manipulate individual cells in laboratory and medical settings. The main challenge is biocompatibility, as hydrogen peroxide fuel is toxic at high concentrations in living systems. Multiple nanomotors can converge on a target cancer cell, delivering therapeutic payloads with unprecedented spatial precision. Researchers are developing alternative biocompatible fuels like glucose and urea that naturally occur in biological systems. Beyond medicine, nanomotors show great promise for environmental cleanup applications. Nanomotors can actively seek out, capture, and remove pollutants from water and soil at unprecedented efficiency. They are particularly effective at removing heavy metal ions from contaminated water through functionalized surfaces. This visualization shows nanomotors dispersed in contaminated water, actively seeking and capturing pollutant particles through enhanced mixing and functionalized surfaces. Nanomotors enhance pollutant removal by 10 to 100 times compared to passive diffusion alone. When multiple nanomotors operate together, fascinating collective behaviors emerge. Large numbers of nanomotors exhibit emergent collective dynamics not present in individual motors. Swarms create enhanced fluid mixing and dramatically improve transport efficiency in confined spaces. This shows a swarm of nanomotors exhibiting coordinated circular motion, creating strong vortex flows that enhance local mixing. The collective speed often exceeds individual motor speed by a factor alpha greater than 1 due to hydrodynamic coupling. Accurate theoretical modeling is essential for understanding and optimizing nanomotor performance. The theoretical framework begins with low Reynolds number hydrodynamics governed by the Stokes equations. The governing equation is gradient of pressure equals eta times the Laplacian of velocity, where viscous forces balance pressure. The incompressibility condition requires the divergence of velocity equals 0. These equations must be coupled with electrokinetic equations and reaction-diffusion equations for the fuel species. The fuel concentration evolves according to the diffusion equation with a reaction term, partial C, partial T equals d Laplacian C minus Kc. Modern numerical simulations using these equations match experimental observations remarkably well, validating our theoretical understanding. Understanding scaling laws helps optimize nanomotor design for specific applications. Velocity scales with length over radius times the catalytic current density J. Power dissipation scales with L times R times versus squared, setting constraints on achievable speeds. Given these scaling laws, how should we design nanomotors to maximize their speed? The answer is to maximize the length to radius ratio and enhance catalytic activity through optimal material selection and surface treatment. This comparison shows that high aspect ratio tubes with large length to radius ratios achieve the highest speeds due to favorable scaling. Despite remarkable progress, several significant challenges remain to be addressed. Fuel toxicity, particularly of hydrogen peroxide, remains a major limitation for in vivo biological applications. Operational lifetime is limited in certain conditions due to catalyst poisoning, tube degradation, and fuel depletion. Scaling up production to billions of nanomotors with consistent quality remains technically and economically challenging. The three key challenges facing the field are fuel compatibility, operational lifetime, and scalable production methods. The field is rapidly evolving with exciting new directions emerging. Enzyme-powered motors using natural biological catalysts offer a path to truly biocompatible nanomachines. Next-generation motors will incorporate sensing capabilities, enabling autonomous decision-making and adaptive behavior. Integration with artificial intelligence algorithms will enable smart navigation through complex three-dimensional environments. Future smart motors will have multiple sensors around their periphery, enabling real-time environmental monitoring and adaptive responses. Professor Solovev's discovery has profoundly impacted the broader field of nanotechnology. This work established an entirely new research field focused on autonomous, self-propelled nanomachines. This achievement has garnered over 1,000 citations and inspired numerous follow-up studies, cementing its significance in the scientific community. In conclusion, Professor Solovev's groundbreaking discovery of catalytic microtubular nanomotors has opened up new avenues in nanotechnology, enabling the creation of autonomous, self-propelled machines at the microscale. Their potential applications are vast, ranging from targeted drug delivery and microsurgery to pollution cleanup and smart materials. As the field continues to evolve, we anticipate significant breakthroughs in nanomotor design, propulsion mechanisms, and control strategies, ultimately leading to a new generation of autonomous nanomachines that can operate efficiently in complex environments.